Physics Q&A. My name is Cora and I will be your host this evening. To start off, we would like to welcome LG Goldsmith and Carson, new and up-and-coming physicists. Our topic for this evening will be centripetal force and acceleration. We will be asking our new physicists a few questions regarding these mysterious topics. The first question is pretty simple. What is centripetal acceleration and force?
Centripetal force is a force that acts on an object that's moving in a circular path, and it has a force directed toward the center of curvature of the path, aka center-seeking force.
To keep the object moving requires acceleration known as centripetal acceleration. This keeps the object moving and is the change in velocity over the change in time. Centripetal acceleration is the acceleration required to keep an object moving in a circle, and it is always perpendicular to the object's travel. The acceleration points towards the center of the circle it creates, also known as the axis.
The acceleration is always pulled towards the center of the circle to allow for a continuous circular motion. The magnitude of centripetal acceleration is related to the tangential speed and angular velocity for a specific object.
Now that we know more about centripetal force and acceleration, we are going to shift gears and create an experiment involving this topic.
Alright, well, we could conduct an experiment regarding spinning an object in a circle and determine the velocity of the object.
Yeah, we could alter that a little bit and spin a bucket with water in it in a circle around our heads and determine the minimum velocity required not to spill the water.
That would be a good experiment. The goal of it would be to find the velocity, as you said, to keep the water from dumping out. Let's go outside and conduct your experiment. Alright, now that you all have conducted your experiment, do you want to explain what you did?
So for our experiment, we filled a bucket with 2.36 kilograms of water and spun it in a circle at different speeds. We recorded how long it took for the bucket to make one full rotation at each of these speeds. We also recorded the radius of Cora's arm and the distance from the bucket handle to the water in the bucket.
We also filmed the experiment and used Tracker to analyze our data.
So how do the concepts of centripetal force and acceleration relate to the experiment that you just conducted?
So the water stays in the bucket because of inertia. The water wants to fly off from the circle, but the bucket gets in the way and keeps it in.
It's kind of like when you go around a tight corner in a car and get squished against the door.
Exactly. When you swing the pail back and forth, you can feel the pail and the water inside pulling on your arm because it wants to continue to move in a straight line, and you want to make it go in a circle. You hold on to the bucket so it doesn't fly away, and the water pushes on the bottom of the bucket. When you swing the bucket upside down, gravity tries to pull the water out of the bucket. Whichever force, gravity or the centripetal force, is stronger will win out. As long as you swing the bucket fast enough, the force of the water pushing on the bottom of the bucket, the centripetal force, will be stronger than gravity and the water will stay in the pail.
Alright, are there any other forces that relate to this experiment besides the one that you mentioned above?
The force of gravity attempts to pull the water out of the bucket and towards the earth.
There's also a contact force between the water and the bottom of the bucket, contributing to the centripetal force, and a contact force between the side of the bucket and the water, preventing the water from continuing on out of the circular path into its own tangential path, like if you were spraying water from a hose.
Okay, so what type of data did we get from each trial?
For the first trial, the speed was equal to 4.14 meters per second. The second trial was equal to 3.34 meters per second, and the third was the slowest trial. That was equal to 1.51 meters per second.
Alright, this looks great so far. How did you guys calculate at what speed the water would fall out of the bucket?
So centripetal force equals mass times velocity squared divided by radius. And we want to find the point where centripetal force equals the force of gravity. So we set Fc equal to Fg, which is mv squared divided by r equals mg.
Continuing with that calculation, the mass cancels out on both sides. We move the r to the other side and take the square root to get v equals the square root of the acceleration due to gravity times the radius. we measured the radius to be 54 inches, or 1.37 meters. And using 9.81 meters per second squared as our acceleration due to gravity, we multiplied g by r and found the square root to get the velocity equals 3.67 meters per second. Any velocity less than this will result in the water falling out of the bucket, theoretically.
Now our values didn't exactly line up with this. The highest and lowest velocities are what we expected, where the first trial had a higher velocity than calculated, which is why the water stayed in the bucket. The third trial with a slower velocity than calculated, the water fell out of the bucket, which was expected. However, with the middle trial, the water should have fallen out of the bucket according to our calculations because the velocity was lower than the required velocity.
Alright, last question for you guys. What possible errors could have occurred during your experiment?
For one, it was difficult, if not impossible, to swing the bucket in a perfect circle, especially when we tried to slow down the speed. If we had done the experiment with the rope, at some point the rope would have gone slack, just like Cora's arm did. Also, our timing of each rotation was done using a phone, and therefore it could be slightly off.
We also considered the accuracy of the tracker application, as it was tracking the bottom of the bucket and each point was placed manually frame by frame. It was impossible to accurately track one specific point of the bucket, and since the bucket was not in a perfect circle, the angular velocity could not be calculated by the tracker completely accurately.